Okay, Chan, what we're just going to go through here is the slides that we showed on Tuesday. I guess that's May 12th. And so there's just a couple of things that we were doing. They are simply speed of the wave. And so, first of all waves have a speed. Sometimes they're faster, sometimes they're slower. So, like the speed on the string that we're showing in the classroom has got its own velocity compared to like the speed of sound. And so the speed of sound is the one that we use most of the time because it's so consistent. Most of the time, within a couple of meters per second, it's 340 meters per second. And so if it gets a little colder, a little bit warmer, it might change. But really, all voices, all sounds are about 340 meters per second. So it doesn't matter if it's, your voice, if it's your mom's voice, if it's somebody else's voice, they all travel at the same speed. They just have different frequencies and wavelengths. And so that's the first thing that we need to know is the speed stays the same throughout a medium. If in fact then your voice goes through a wall, well then it's going to change the speed of the sound because it's going through a different um, um, object, and so it takes a little bit of the speed away, or it may actually become faster because there's more things for it to collide into. But we didn't go through that, so we just know that speed does not change. And so whenever you get a speed of one wave on one string or one wave through sound, it should be the same. All right. And then we learned the velocity or the speed of the wave equation. So it's down here. Velocity of the wave equals its frequencies times its wavelength. And that's the one equation that you're going to get on the test. That means that we can always calculate one if we only have the other two. So if we have the frequency and the wavelength, we can tell what the velocity of the wave is. And this is kind of a little bit different from what people are thinking about. Remember, frequency is how fast it's going up and down or changing. Wavelength is how long that wave is. And then velocity is like the same velocity that you and I talk about when we're driving a car. How long is it going to take for that voice to go from my mouth right here to like the other side of the room or to the other side of the city? And so every every sound, every wave has a speed. And so we'll just use that equation V equals F times wavelength. And if you get an equation like this, we're all really good at this stuff by now. It's a 4-column method problem. The wavelength is 0.25, the frequency is 20. So what's the velocity or the speed? So you just write down V equals F times wavelength and solve for V. And you can imagine that we can have a lot of different versions of this where we tell you what the velocity is and the frequency, and you have to solve for the wavelength. But the bottom line is, you guys know how to do these problems, and so I'm not going to spend too much time on this equation, but it's worth 4 points or 8 points on the test, so you should know how to do it. All right. The next thing we learned about it was standing waves, and this is kind of hard to see if you're not in the classroom because we have a demo of this happening in the classroom. But what would happen is if we have a wave and we have a wave generator on one side and we have the string tied to the other side, we can put a wave through the wave and the wave will bounce back. So if, let's say I had here on the screen, let me see if I can find my cursor here. Okay. Um, right here, if I had something driving this, so I had something that was making this go back up and forth, like my hand is like making this wave. The wave will go through the string, bounce off of here, and then start bouncing back. And so what normally happens is the waves keep bouncing back and forth between them, and they constructively destroy each other, or they constructively build on each other, or they destructively destroy each other. And so all we do is usually experience is just shaking. But every now and then we do it just perfect so that we get what's called a standing wave. And so a standing wave, I'm going to go real quick to the second page right here. The first standing wave looks like this right here. It looks just like one bump. And this wave is what we call the fundamental standing wave. It's the first one. It's the one driven by the least amount of frequency. And so this is when all the waves are building on each other. If we move over here to the second fundamental or the second harmonic, this is the second one where, again, these waves are going to build on each other. So what we do is we start out, we put like a frequency in. So in the one that we were building on, we put about 8 hertz into this, and we were able to drive the first one. Okay, and so for the string would just look like flat and it would be bouncing a little bit. And all of a sudden it would go boom and it would look like the first fundamental. And so that was about at 8. And then if I put it up to 10, all of a sudden the string went flat again. And so all those waves are going back and forth in the string and they're not building on each other, they're actually destroying each other. And so all we get is shaking. That's what a normal bridge feels like. But then if I got up to 16, if I got to twice the 8, 2 times 8, I would get what was called the second harmonic or the second fundamental or the second standing wave. And so that looks like this right here, this second wave right over here. And this should remind you of the Tacoma Bridge where the dog died, where the bridge was like going crazy. It was going back and forth because it was being driven at its perfect harmonics natural frequency. And therefore, the wind was creating all these waves through it. And instead of the bridge just shaking, instead it started to go into its standing wave or its harmonic. And so, harmonics are natural frequencies that we oscillate at, and they are different for everything. They're numbered by how many antinodes there are. And so the fundamental is the lowest. So what are these things called? Antinodes and nodes. So on this example right here, we've got the nodes right here. It looks like nothing is happening at this string right here. Doesn't look like there's any movement. All right. But the antinodes looks like there's really wide movement. So there's this big gigantic flex back and forth. And so those are the antinodes. And so if we look, we can count out the nodes 1, 2, 3, 4, and we count out the antinodes 1, 2, 3. If you want to know what this is usually what see what's happening in a tube. We see a standing wave build in a tube, and this is like for instruments and stuff. But we're going to concentrate just on the strings because the strings are easy, and we just want you to get this idea of what a harmonic is. So a natural harmonic, or the first harmonic, is the first one. It's this one that has just one bump. All right, the fundament is called the fundamental. It's the lowest frequency. It's called the first harmonic. There's only one bump. And one of the things that we need to understand is that there's only half of a wavelength in the first harmonic. Because if you see this, there's only one half. A full wave looks like this. One all the way down to here. That's a full wave. So what we have in the first harmonic is only a half of a wavelength. And so the first, or the fundamental harmonic, is only a half of a wavelength. And then after that, we can just see them by looking at what their picture looks like. So if we look at the second harmonic, we can see a full wave here. If the third harmonic, we can see one and then another half. So we have 1.5 waves. And in the fourth harmonic, we have 2 full waves. Okay. All right. So there we gave this one equation right here. How do you find out the harmonic? So when I was driving that string on a wire, I knew that the first harmonic, I just had to play with it until I got it. It was about 8. So let's say it was 8. And I got the string to do what it looks like as number 1. And then as soon as I went off of 8, it went back to nothing. So I knew that if I wanted to do the second harmonic, I just had to multiply 2 times 8. And so in this example right here, this string is being, its first harmonic is at 12. And so to find the second harmonic, we'll just multiply by 2. And if we want the third harmonic, we'll just multiply by 3. So pretty simple. And the way that the equation works is it just says, okay, if you want to know the harmonic of like the fifth, so let's say I want to know the fifth harmonic right here. I want the F of the fifth harmonic. I would just do the fundamental times 5. If I wanted the sixth, I would just do the fundamental times 6. So if I wanted the sixth harmonic, I would just do 12 times 6. And that's what a standing wave does. And it's pretty predictable, and we saw that in our example in the class. Okay, waves need to be determined by just how they look. Okay, so you can use that equation to solve for some of these things. Lots of examples of when harmonics really work. Here's one where they're looking at the waves that go through a bat when you hit them in a certain spot, and then where that wave is going to be at its highest. And if so, is that wave going to be moving down the bat like at your hands? And so if that wave is at its biggest at your hands, you're going to feel that your hands are going to hurt. Or if you can be at a node, well, then your hands won't feel that wave going through the bat, and so you can get less pain, I guess. Right. All right. So you can look at all these videos. The worksheets are on. We gave you guys the worksheet. So worksheet 2 is on the back of worksheet 1, and then worksheet 3 is available to you from the sub today. So do we have a quiz on Friday? Quiz 9.2 will cover all of these topics. I will be here back on Thursday. So if there is a question or you don't understand something, you can always contact me. All right, have a great day, and I will see you guys on Thursday or Friday.